Hello, Didier Stevens here, analyst at Enviso. In this video we are going to look at an interesting malicious PDF document because it has several layers of different types of malicious documents. And this video is also a bit different than the usual analysis that we publish. Here we will do this on a pristine machine, a pristine Ubuntu machine. So there are no tools whatsoever installed that we need for the analysis, so we will also install them as we go. So the PDF that I have here is remittanceinvoice.pdf.vir. I did append the extension .vir. That's what I always do with files that are malicious or potentially malicious. Not only does that clearly indicate that it is malicious, a virus, vir, but it also prevents me from accidentally opening this. So the tools that we need, you can find them on GitHub in my suite, Didier Stevens suite, and we are going to copy this. We are going to clone this with GitHub. So command git clone the URL, okay, and this fails because the git command is not installed, a command git not found. But Ubuntu proposes as a command to install this sudo apt install git. Well, that is what we are going to do to install git. Like this. I provide the password and I install git. That is done now, and now I can try the command again. And here the repository is cloned. So if we look into our malware directory where I'm doing the analysis, you can see a folder Didier Stevens suite, and inside that folder all kinds of tools like the PDF tools that we need here. So most of these tools are Python tools. So I'm starting in the Python 3 interpreter. I provide the folder PDF ID. That is the tool that I'm going to use, and I give it the PDF to analyze. Now PDF ID is a simple tool that I use for triaging PDFs. It gives me a first ID what is inside the PDF, and then I can decide if it requires further analysis or not based on its output. And if it does, I will use PDF Parser, another tool, to do the analysis. So what PDF ID here shows is a lot of keywords, names like page, encrypt, and so on. And it does this with counters. So for example, keyword embedded file, name embedded file is 1. So that means that somewhere in the PDF file that name here / embedded file, that keyword is found. So that means that there is an embedded file inside that PDF. So that's something we definitely need to look at. Other keywords are 0. That means that nothing was found for that keyword. So for example, launch 0. Now you can make the report smaller by using option N, and then you only get the keywords that are not 0. N stands for not 0. So we are interested at what we see here after the start xrf here in this case. And so we have an embedded file. That's important. An open action, so something that is launched automatically when the PDF is opened. And then also OBJSTM. Now that is important to know about and to take into account OBJSTM stands for stream objects. So that means that inside the PDF there are not only objects, and we will see them later with PDF Parser, but also stream objects. And stream objects are special objects that can contain other objects. And the objects they contain can be compressed. And since PDFid is a simple tool that searches for particular strings, it is not able to deal with compression. So if objects have been compressed, PDFid will not find them. And in that case, it is recommended to also do a statistical analysis of the PDF with PDF Parser. And that is what we are going to do here. So Python 3, PDF Parser, the document, and option A to produce statistics, and option O, uppercase O, to also look inside stream objects, and so to decompress the content of stream objects and take that into account. Okay, so and here we have different statistics, and at the end also the keywords, like embedded file, open action, acroform that we saw. So we see here embedded file 1, and now we also see which object represents that embedded file. That is object 28. Objects have indexes, we will see that. But what is also appeared is JS and JavaScript, object 7. So that means there is also JavaScript inside that PDF, and that is something that we did not see with PDFid, because those are hidden, kind of, in those stream objects. If I run the command again, but without the O, you see, I get more or less the same output as with PDFid. JavaScript is not recognized. But if I run it with that option to look inside the stream objects, then we see the JavaScript. Now, embedded file 1. So there are different ways to take a look at this object. I can do, for example, a search for embedded file. And embedded file. And the search option here is not case sensitive. So I can just type everything in lowercase, and the leading slash is also not required. Okay, and so one object was found that contains that keyword embedded file, and that is object 28. That's something we also knew from the statistics. Another way to select that object would be to say select all objects with index 28, and then we have that object. So this object here contains a stream. That stream is not shown. That is binary data, and that is the embedded file that is inside the object in the stream. But we see here Filterfletty code. This means the following. All the streams and all the binary data associated with objects can be transformed. For example, that data can be compressed. Transformations in the PDF language are indicated with filters. So a filter means that the data was transformed. Flet decode means that the data was deflated. Deflated means zlib compression. So with this here, Filterfletty code, we know that the stream that we have is compressed. To decompress it, we just need to use option F. F stands for filters, and this will apply all the necessary filters. Now there will be a lot of output, so I'm going to pipe this through less. And then we get this. So again, we get the output. And then here we get a Python representation of the binary data that is decompressed. And as you can see, it starts with pk and then byte value 3 and byte value 4. So that is very typical of zip file containers. So this is probably a zip container here that we are dealing with. Now if we go back to the statistics, there was also JavaScript involved in object 7. So let's take a look at object 7, and we again need to use that option O, uppercase O, to look inside the stream objects, otherwise we will not find it. Okay, and here this small JavaScript is typical for launching automatically embedded files. So this JavaScript is an action, and if we would search further in the PDF, we will see that it is related to the open action. So if I do, for example, a search for open action is a reference to object 7, and indeed object 7 is a JavaScript object, and this is JavaScript that is executed. What this JavaScript will do is when the PDF is opened, then the embedded object will be written to disk in a temporary file, and there is no control over the place where it will be put. It's in a temporary folder, and then the corresponding application will be launched, and we see that here with this value and launch 2. Now the name of the PDF, of the embedded file is a bit strange, has been verified, however PDF, JPEG, XLSS, .docx. So this is maybe to mislead the user that will open this, because if you open that PDF with Adobe Reader, you will get first a pop-up. Adobe Reader will ask you for permission to extract and launch the embedded file. So it is a docx file, and that corresponds with the PK0304 that we saw. So for zip, because docx files are essentially zip containers. So we will extract that embedded file now that we know more about it. So here, with this command that we did, we can see the content on the file on the screen. If we want to dump this to disk, we use option D, and we give it a name, like for example embedded docx.vir. And now this file has been written to disk. It is a docx file, so it's very unlikely that it will contain macros. Docx files don't contain macros. So if I would run oledump on this file, oledump is a tool essentially to look for macros, to analyze macros in Office documents. Here you see no OLE file was found, because macros, even in the docm file format, macros are stored inside OLE files. So that's not the case here. So what we are going to do here, since this is a zip container, we will look at the content of the zip container. And we are not going to just decompress this with a classic zip tool. We are going to use an analysis tool, a malware analysis tool for zip files that I developed, and that is called zipdump. So let me run that. And so here you see all the files inside the zip container, and then also their timestamp. Now, this is unusual. When an Office document, docx or docm or xlsx, that file format is called OOXML, the Office Open XML file format, which is essentially a zip container with a lot of XML files and sometimes binary files like images or macros inside OLE files. When Office creates a document like that, all of the timestamps should be like this. So the 1st of January 1980, and a timestamp of 0. Sometimes it can be 1, but you should have that. The fact that we have other timestamps here can mean two things. Either that this file was not actually created with Office, but with another tool. For example, if I remember correctly, it is OpenOffice or LibreOffice who will actually have the timestamp here of the creation time of the document. So that is one thing. Another thing could be, and that is more the case with malicious files, could be that the file was indeed created with Office, but that it has been tampered with, that it has been opened with a zip tool, make some modifications to it, and then save it again. And then for all the files that have been changed, you will have the timestamp of the change. Now, if we look at all the timestamps, there is one that is very recent, this here. So at the time of recording this is just 2 days ago. So this file here, which is an XML file, was most likely modified after this document was created. So I'm going to look into this one here. So you don't need to remember the name, but the index. The index is something that the zip tool generates. It's not metadata of the zip file, it's just a convenience index that zipdump generates, so 14. So I can select a 14. And then, for example, let's do an ASCII dump, hexadecimal ASCII dump, because I'm not sure if it is really XML. But indeed, it looks like to be proper XML. So let's do a binary dump so that we really see the XML. Okay, yeah, and this indeed looks XML. Now inside XML here, there are URLs, as you can see. And as it is presented here, all in one line, it's hard to find the different URLs. So to deal with that, again, I have a couple of tools that can help us. I have, for example, a tool that is called XML dump, and it can do different kinds of transformations of XML files. And one of the transformations it can do is do a pretty print. Now notice here that I'm piping these two commands together with the pipe character here. So this command is producing the XML file to its standard out, and this command here will read that XML file from its standard in. Many of my tools can also accept input from standard in. And now we have a more readable presentation. We see here all these URLs, which are typical for Office, and they are normal. And then we see here one that is a bit more suspicious, this URL here, and also the target mode external. Now, if you see something like this in this file, in this relationship file, it means that the docx file contains a template, that it has a reference to a template. And that reference to that template is external, so the template needs to be downloaded from this URL. And that's what we are going to do as a next step in the analysis. But I first want to show you another tool. I also have a tool that can do searches in text files based on regular expressions, and it comes with a library, a small library of built-in regular expressions, and there is one for URLs. I can say Option N, name URL. This will select the regular expression with name URL and apply this. And then here we have all the URLs. Now I don't think here there are any duplicates, but if you would have duplicates, you can also eliminate that with option U to have a unique list like this. And then, yeah, you filter out all of the ones that are to be expected. Now, if you are not familiar with Office XML documents, the inside of those XML documents, you can also apply a built-in filter that comes with our research, and that is specific for Office URLs. So all typical Office URLs will be filtered out, will not be displayed. And so what we keep are the unusual URLs. As you can see here, we have this URL. That's another method to figure out the URL here. Now to recover, to get that URL, we will download this. And so let me copy the URL. I must be careful not to click it. No, I didn't. Try again, like that. Okay, I copy the URL. Yeah, there. I have the URL. So I'm going to use curl to try to download that URL, and I'm going to do that over the Tor network. So SOX5, that is the local proxy that we are going to use for Tor. So that's on the local host on port 9050. And when I download, I also want to keep the headers, so that's with that option, save the headers to a file. And as I expect to do this several times, because often it doesn't work from the first time, I'm going to add a counter for each download so that I can keep each file. And then the download here, I will call this malware. Well, downloaded malware.vir. And then the URL. Okay. Now this did not work because curl is not installed, so we need to install curl. Let's do this. Okay. And let's try this again. And now we get an error, connection refused. That's because the port is closed, so that means that Tor is not installed. So I do need to install Tor first. That's what I'm going to do. So the reason that I want to use Tor to download is not to give away the fact that I'm trying to download the sample from to the malicious actors, because here I'm using curl, and curl has its own user agent string, so that can already be a giveaway to them, and then they might be interested in the IP address that I'm using, the source IP address, and block that, for example. So that's something I want to avoid. So okay, Tor has been installed. Let's try again. Nothing is being downloaded, apparently. Okay, let's see what we have. Okay, we do have headers. Let's take a look at the headers. Okay, and the headers tell us here 301 moved permanently. And so that's where we actually have to download the file. And you can see it's a doc file. Okay. So I'm going to launch the curl command again, but with option L, uppercase L. That is the option to follow redirections, like the move permanently. And I'm going to increase the counter here, and I notice I did not add a counter for the downloaded malware, so I'm doing this here now. Okay, so the reason why I'm just increasing the counter is so that I don't overwrite files that I just created. So okay, and it looks that this worked. Something was downloaded. And indeed here downloaded malware 2. Let's take a look at the headers. Okay, yeah, so this was indeed redirected, and then here content type MS Word, so this should be a Word document. Let's check this by running oledump. Well, I'm just going to type the command again. Oledump on downloaded malware 2. And it is not a valid OLE file. So if we get this error, not only do we know it is not an OLE file, but also that it is not an OOXML file, so it's neither a zip container. So I'm going to use the file command to try to figure out what it is. And it appears just to be text. So I'm going to do a binary dump, an hexadecimal dump, sorry, of that file to look at the beginning here with piping this output to head to only have the first 10 lines. Okay, and this is actually a very obfuscated rich text format file, an RTF file. The reason why I say it's heavily obfuscated because of all these things that I see here, and also because it doesn't say RTF1. So normally an RTF file, a rich text format file, should start with this, curly brace open backslash RTF1. But here it just starts by backslash, curly brace backslash RT. And this is not according to the specifications, so that is not a valid RTF file, but Word is able to read this nevertheless. So Word will read this file. So, and that is for me already a very strong indication that this is malicious, because this is a obfuscated RTF file. So I have a tool specific for RTF files. So Python 3, rtfdump, and so downloaded malware. Okay. Now we get output like this. First of all, if you get output like this, it means that it is indeed an RTF file and that rtfdump is able to process it. Now RTF files, let's look at it with less, because it's a pure ASCII format, unless it has been tampered with. So downloaded malware. Yeah, indeed there. Yeah. As you can see here, a lot of nested curly braces. And then a lot of hexadecimal data. So this is typical for RTF, a lot of nested curly braces, but this should be not so spread out. So this is obfuscation that is being done here to make the analysis more difficult. So you have all these nested curly braces, and what rtfdump does is show you all of those levels. So here we have level 1, level 2, and so on at different levels. This goes really deep, and then here it comes back. And you have different objects inside here. So let's see if we have indeed objects that rtfdump recognizes, and we do that with option O, uppercase O, and to filter out the objects. But unfortunately, rtfdump doesn't find any objects. Now the reason we are interested in objects is that RTF files by themselves cannot contain VBA code. So they will typically contain exploits, and exploits are typically put inside objects, and objects are represented with hexadecimal. Now rtfdump is not able to recognize the object here, so that's because of the obfuscation. We have to work around that. And if we take again the output here, this column here, age, this is a counter that tells you for each level of curly braces how many hexadecimal digits there are inside. So okay, this is level 1, that's the complete document, but then the first nested curly braces entry here inside that complete object is here, level 2. It actually has a name, so you see it's actually an object. And there are 8,349 hexadecimal digits. Now, you would expect an even number, because each byte, a byte has to be represented with 2 hexadecimal digits. Here it's uneven, so that's another indication that we are dealing with obfuscation. So what I'm going to do here is select this entry, entry 2, and try to decode the hexadecimal code. So I'm selecting this, and again this will produce a lot of output, so I'm going to pile this through less. And as you can see here, the content between the curly braces for that entry is selected. And if we go down, yeah, here we can start to see hexadecimal data. But it should be, in a normal RTF document, it should not be separated, those digits should not be separated by all these new lines. So that is indication of obfuscation. So next what I'm going to do is instruct rtfdump to do hexadecimal decoding. That's with option H, uppercase H. And now I'm getting output like this. If you see a lot of FF like this, this could be an embedded OLE file, and it happens often that you find objects inside malicious RTF files that are OLE files. But then we should see something like root entry here, and I don't see anything of this. I don't see anything recognizable. So let's go back. And now here I see this sequence D0CF11E0A1B11AE1. That is actually the magic header of an OLE file. But that should start at the beginning of the byte, so not the second nibble, but the first nibble. So because of the obfuscation that rtfdump here is not able to handle properly, at some point here the hexadecimal digits are shifted by 1 digit, and then everything is skewed. Now I have an option to deal with that, and that is option S, to shift the hexadecimal digits by 1 digit. And if we do that, then we can already see something else. Here we see a readable string, and now here we can indeed see the normal magic header. And here FFs, that could be the file allocation of an OLE file. And here we see root entry in Unicode. So root entry, that is something that you will always find in an OLE file. And here we see OLE10 native with a special casing. That is often present for embedded objects. So this is indeed an embedded object, but it is so obfuscated that rtfdump is not able to recognize it, and that we have to guide it manually to find back the object. So let's see now, by using option I will produce info for the embedded object. Let's see if that works, but it fails. rtfdump is not able to recognize the object, so we need to extract it ourselves. So let me go back to the hexadecimal ASCII dump. And so the object OLE file starts here, because that's the magic header. It's easily recognizable. If you have a bit of imagination, those hexadecimal digits here, the 8 first hexadecimal digits, well actually the 7, read as doc file. So D0 is DO CF one is I, one is L, so doc file. So that is what we need. We need to extract the byte sequence starting from here, and that is as position hexadecimal 40 and 7. So that's 47. So I'm going to cut out the data with Option C to cut out the data. So starting from position hexadecimal is position 47, and then all the way till the end. So the colon with nothing, that means everything all the way to the end. If I do that, I have again an hexadecimal ASCII dump that starts here with the right magic sequence. So I actually need the binary data, so I'm going to do a dump and write this to a file. Let's call this ole.vir, and then let's see if I can run oledump. And indeed, it is. We were able to extract a valid ole file, and we defeated the RTF obfuscation. And we here have a stream, ole10 native. So let's look inside that stream by selecting it. It's stream number 1. And here we have nothing that I recognize. This just looks random. Let's see by trying to extract the strings with Option S, uppercase S, so to extract the strings. Yeah, nothing recognizable. Now, what happens often with RTF files is, like I said, is exploits. And exploits often means shellcode. So this could be obfuscated shellcode. And there is a rather easy way to figure that out. And that is with a tool that I like, the shellcode emulator, ascii. Here you have that tool developed by David Zimmer, a very useful tool. This is a tool that is able to emulate, it will not execute, but it will emulate 32-bit shellcode designed for the Windows platform. Now, unfortunately, the Linux version of the shellcode emulator is no longer maintained. We actually need to use the Windows binaries. So I'm going to download them. Okay, save this. This is the tool that we need. So I'm going to drop this in our working folder, where we have our different samples, like this. Okay, now this is a Windows executable. We cannot run this on Linux, Ubuntu, unless we use the Windows emulator Wine. Wine is not installed, so I'm going to install it. Like this. Okay, so this might take a bit of time. Yeah, accordingly it will take around 5 minutes, so I will cut this out of the video. Okay, and we got an error in the installation here. So when you get an error like this, it could mean that you have to update all the references of the packet manager, and that is something you can do with the following commands. sudo apt update, and indeed it is doing some updates. So that is actually not updating the packages themselves. That's something you have to do with upgrade, but this is updating all the information necessary to do this. So once we have done that, we can try again to install Wine. And it is indeed now resuming from where it left off. Okay, Wine should be installed now. So let's taste some Wine. Indeed. And if we run it to emulate the shellcode emulator, okay, we are getting some messages. Okay, messages from Wine itself, but that's not a problem. And then here we get the output from the shellcode emulator. So I'm going to run the shellcode emulator. I give it as input the file. Well, actually, let me check. ole.vir. Python 3. Yeah, so that is the OLE file. So what I actually need to do first is select that stream 1, produce a binary dump, and write this to disk ascii shellcode.vir, because I'm suspecting that there is shellcode in here. And now I can run Wine shellcode emulator ctbg and give it as input the shellcode here. Now, if I'm going to run this, this will probably fail because I don't know what the entry point is of the shellcode. So I don't know at which address the start of the shellcode is located. But that's not an issue with the shellcode emulator, because you can use this option, find shellcode, find ascii, and this will do all kinds of, so this will try at all different possibilities of entry points to find potential entry points. And then I also want a report with option R, like this. Okay, so shellcode emulator was able to find 8 different possible entry points. And it does this by emulating at each entry point and then reporting what of API calls it is doing. So, and the fact that it starts with a get process API call is really good, because that is typical of position independent Windows 32 shellcode. So what I'm going to do here is just try out with the first one, 0. So I'm going to type a 0 here. And so it is at position entry point 95. So 0. And indeed here we have a summary of all the API calls that the shellcode would execute. So the shellcode emulator did not execute these API calls, but did it emulate them. And here we see a URL from where something is downloaded, and then where it would be written to with the URL download to file W, so the Unicode version. So that is typical of shellcode that downloads something and executes it. As you can see here, it also tries to look up the address of shell execute to execute it. So what I'm going to do next again is download this with Tor. So let me copy this. No, actually, I can see that I could actually just do copy link. Now, right before we do that, I want to come back to our stream here. So I'm going to do an ascii dump like this. And so at position 97, so if I remember, or 95, so somewhere here should be the start of the shellcode. And what's in front of here could be a data structure or anything that is exploited with an overflow, for example. But I don't recognize anything of this. This, for example, doesn't look to me like a typical equation editor vulnerability. I'm more familiar with them that I would recognize, so here I'm not recognizing it. But that's not an issue, because as you can see, the shellcode emulator here helps me to discover the shellcode and tell me what the shellcode does, even if it is obfuscated. Because we don't see an URL in here, but the shellcode emulator is able to do the obfuscation by emulating the deobfuscation steps and then presenting us with the URL. Okay, so curl socks5 localhost 9050, dumping the headers, dumping the file, so mal downloaded malware 3. It should be an executable, extension vir. Do follow redirections and then the URL here without a comma. Let's try this. Okay, should you like this? I made a typo and the file was indeed downloaded. Yeah, 1 megabyte. Let's take a look at the headers first. So a Windows executable, there was no redirection. Let's try file. And indeed, it is a Windows executable, actually a .NET executable. So here I'm not going to do the analysis of the executable itself. I'm just going to calculate its hash, like for example MD5 hash, doesn't matter which hash you use, because we are going to look it up on VirusTotal. Let's search for that hash. And here indeed it is something known with a lot of detections. And if you go here into the community, the analysis, several of the analysis will tell you that it is the snake keylogger that was downloaded. Now, if the file is not found on VirusTotal, yeah, you can decide if you want to upload it or not. And if not, you could try to scan it yourself with your own antivirus, like for example the open source ClamAV, which is not installed. So sudo apt install ClamAV. Okay, and now I can run a clam scan, and actually let's just scan everything with extension vir. And it doesn't detect anything, everything is okay, so its definitions are not updated yet so that it would detect this malware. So what we did here is go through several layers of embedded files and obfuscation using open source tools to do a static analysis, and I also showed you how you can install those different tools. Hello, we are 2 days later, and I took a second look at the exploit, and now I'm convinced that it is an equation editor exploit, the well-known CV 2017-11882. So if we take a look with oledump, so selecting stream 1, here you see 0108, so byte values 1 and 8, and this is typical for a CVE 2017-1182 equation editor exploit, because these are the records for a line and a font name record, and it's in the font name record that the exploit is, the overflow is. So you have 2 bytes that follow that indicator for the record, and then after 2 bytes here you have the font name. If I'm not mistaken, maximum 32 bytes, and here, in such case of an exploit, this should be shellcode without any null bytes. It cannot contain null bytes because a null byte is a string terminator, and if there would be a null byte, then the string would terminate and would not be able to overflow the buffer. And also here, one of these trees here is the start of the header for the METF format. So record font name, first byte, second byte, and then here the font name itself, so that's position E. So let me cut that out. So starting at position E, and so if I remember correctly, 32 bytes long, that's what we have. Okay, so I'm going to do a binary dump and disassemble this with the NASM disassembler, and disassemble 32 bits we are going to disassemble and read from standard in. It is not installed, so let's install NASM, the NetWide assembler. That's it. Let's run the command again, and indeed we have shellcode that calculates values here, addresses that are then called and do. The reason why it is calculated as follow is so that it doesn't contain any null bytes, as you can see. So this indeed shows us that we are dealing with an exploit with shellcode, and we found the malicious shellcode itself. This is just the jump shellcode, and that is an equation editor exploit.